Good morning. Today is January 25th, 26th, 2012, and this is going to be the lecture for the section 9.2. We got a start yesterday, but it's a weak start, so we're going to do a redo and record this from the very, very beginning. Again, as you come in, make sure that you stop by your hanging folders where there is a new scaffolding sheet that I'm making reference to. You're also going to need your probability tables and your calculator as we work through these problems. Okay? We had said in the first lecture for this chapter that we laid down the basics of this idea called testing a claim. And the claim was going to be tested through some sort of calculation, and I hid the calculations part. We just looked at the numbers at the very end and said, oh, look at that p-value. It's too big. We failed to reject H0. Oh, look at that p-value. It's small enough. We get to reject H0. We talked about all the vagaries having to do with that. Now it's time to actually dive into the numbers and actually do some mathematical work and complete the circle. All right? So today, in particular, though, we're only going to be talking about claims about population proportion. Okay? At the end of this, we should be familiar with, you should be starting to memorize the conditions associated with a test of population proportion. We should be able to actually conduct those tests using the infamous four-step process. And we should be able to take a look and see the relationship between this confidence interval calculation that we're making and something that we had done earlier, which was calculating confidence intervals having to do with the same kind of information. So let's get started. All right? I'm going to be constantly referring back to the idea of comparing what we were doing to the stuff that we did in the first section. Again, looking at p-values, comparing them to alpha values, making claims of either rejecting a null hypothesis or failing to reject a null hypothesis. We'll also take a look at the differences in performing these tests when they're one-sided or two-sided. Remember that the one-sided tests involve claims of greater than or less than, but the two-sided tests involve claims having to do with not equal to. All right, so let's go back to the problem that we talked about in 9.1, and that is a free throw shooter who claims that they're an 80% shooter. You don't believe them. You want to prove them wrong. And you want to look at what evidence exists against that claim. We said, make this person shoot 50 shots. And in this particular instance, they make 32 out of the 50 shots. And we asked the question, is that 32 out of 50 convincing evidence against the claim that they're an 80% shooter overall, if you look at all of their shooting over a lifetime? We talked about converting the statements into the notation of statistics, H0 and HA. We talked about in the quiz that you took yesterday saying it's really important to specify what is it we're measuring, how we're measuring it, and then how are these comparing to the claims that are being made. In this case, what's the population that we're talking about? Oh, the population of all this person's free throw shooting. What's the parameter we're talking about? Oh, the parameter is either an expression that starts with the word mean or an expression that starts with the word proportion. In this case, we're looking at the proportion. Proportion of what? Baskets made. And then lastly, we finish this up with the statement, well, what's our null hypothesis? What is that statement of no difference? Or what is that statement that we don't think is true? What is the alternate hypothesis? What is that statement that we've tried to prove? pretty similar to your quiz from yesterday. Now we're going to go back, bring back some ideas from a previous chapter, tie it all together. In order to go from the data, 32 of 50 shots made, all the way to the end part, which is the conclusion, which is, do we reject H0 or do we fail to reject H0? In order to make that path, we're going to do some things that we did before. We're going to check conditions. Now, what do we mean by checking conditions? We mean that before we can do any calculation, we have to make sure the assumptions based on those calculations are fulfilled. These are the same conditions that you are already familiar with from earlier chapters. Unbiased, independent, and normal. We want to make sure our sample is unbiased. What does that mean in this case? Do we think that those 50 shots are really a random sample of all that person's free throw shooting? I think that's reasonable. Do we think it's independent? Do we think that each free throw shot is independent of an independent sampling? Do we think making some increases the probability that they're going to make some on the next throw? Do we think if they miss it, it decreases the probability on the next throw? Okay. Let's say for the sake of argument that these trials are independent. And then lastly, normal. I would like to be able to use the great normal distribution tools that we have at our fingertips. All right? So we can view the 50 shots as being an unbiased sample of all the person's free throw shooting. We can determine whether we believe the sampling distribution, the distribution of sample proportion, is normally distributed. And we're going to use the same test that we did in chapter, is it chapter 8? I think it was in chapter 8. And that is, a distribution of sample proportion is normal if n times p is greater than or equal to 10, and n times 1 minus p is greater than or equal to 10. We translate that as, do we expect at least 10 successes? Do we expect at least the person to hit at least 10 baskets? Yeah. Do we expect them to miss at least 10 baskets? Yeah. Okay. By the way, I think what we'll do is we're going to be a little bit more explicit here. It's going to look more like n times p, which is equal to 50 trials with a probability of success of 0.8 equals, we expected 40, and 40 makes, and 40 is bigger than 10. N times 1 minus p is 50 times 0.2, which is 10. And 10 is greater than 10. Sorry, greater than or equal to 10. So let's be, when we talk about doing this in the four-step process, let's get that level of specificity. Okay, and then again, lastly, that independent. Now the independent one, we think of each of these trials as independent, but the other way we tend to attack the independent condition is the population greater than 10 times sample. That works when we're doing sampling, like I've got a group of people, and I'm grabbing them. I'm grabbing them one by one, interviewing them, in order to make sure that things seem independent. We just have to make sure the population is so big that grabbing one individual doesn't change the probability. All right, let's continue on. Okay, carrying out the rest of the significance test, assuming that we've met our conditions, involves doing some calculations. Again, the basis of these calculations we already talked about in chapter 8. We believe that one sample is just one of many samples of size 50 for that free throw shooter. We think that their sample proportion, in this case, I think it was, what was it, 32 out of 50, so 64%, that sample proportion, or that p-hat, is just one p-hat of many, many p-hats. And all those p-hats make up a distribution of p-hats, a distribution of sample proportion. Because every sample proportion is unlikely to be exactly the same, they make up a distribution. That distribution has a mean, and that distribution has a spread. And because we already checked the condition, the distribution has a shape. The shape is normal. So let's recall from chapter 8, what is the shape of the distribution of sample proportion? Normal. What is its mean? It's the population mean itself. If there's an 80% shooter, the center of all those p-hats is also going to be at point A. And what is its standard deviation? It's the square root of p times 1 minus p all over n. That means that if I'd like to draw that out, I guess I'm going to have to do a little calculation to find out what the spread is for that. Spread is going to be the standard deviation of the distribution of p-hat is going to be 0.8 times 0.2 divided by 50. And on my calculator, that ends up being 0.05. Oh, it's right there. Yeah. Now, where's our p-hat? Where's our p-hat when the person made 32 of 50? It's way down here at 0.64. Now let's tie that back to the definition that we introduced in section 9.1. Let's think about calculating that p-value.
Where do you get that?
Well, remember when you challenged me to actually prove that I was an 80% shooter? I went and I made 50 shots, and I made 32 of them.
All right.
That's our p-hat. So what's the probability that I would get 0.64? But according to our definition of p-value, it's not just 0.64, but 0.64 or more extreme. Well, what's more extreme than 64%? All the stuff below it. Because when Jason challenged me to do the free throw shooting, we went to the gym and I shot 50 times and I only made 32 of them. 32 divided by 50 is 64%. So that area that I just shaded in, that's our p-value. Now, if we only had a way of actually calculating what that p-value is.
What you do.
But what we do, because we know it's from the normal distribution. We know the mean of that normal distribution, and we know the standard deviation of that normal distribution. Okay, so what I'm going to do is I'm going to wipe out all the drawing. I'm going to go back to what the book has to say about this, and we're going to go and show this all off. Okay, so here's our sampling distribution, the distribution of all p-hats, assuming an 80% shooter and 50 shots. By the way, how did I know what the center of that distribution of p-hat was?
It's your null.
Because it's my null hypothesis. Because the definition of p-value says it's the probability of your sample statistic being that extreme, assuming that your H0 claim is true. Assuming the null hypothesis is true. And our null hypothesis was proportion was 0.8. Okay? So, we've got this new intermediate step that is coming in right now. And that is this thing called the test statistic. We were on the way of calculating that just a second ago before I switched over. Okay? How would you calculate the probability of shooting 64% or less, given the assumption that the shooter is an 80% shooter? Well, you would have calculated a z-value, and then you would have looked up on the z-table and changed it to a probability. Okay? We are going to call the z-value in this case, we're going to give it a special name, and we are going to call it a test statistic. We are going to say, in the process of testing this claim, we get a test statistic, in this case a z-value. If you would like to, you may think of a test statistic as a way of measuring the rarity of something. We know that values of z that are around 0 aren't rare at all. They're quite common. It's about being average. But if I told Paul that the z-value associated with his hilarity was 4, that he was 4 standard deviations above the mean when it comes to being funny, this is Tom. Okay. I'm very sorry about that. I thought I did. I'll get it corrected as soon as possible.
Speak for yourself.
Okay, bye.
Cliche.
Great, I'm in trouble. All right. So, and I might say the same thing about myself in terms of being able to bore you to sleep. I'm probably maybe not even a 4, maybe a 5 or a 6. Standard deviations above the mean. You're not supposed to agree with that, Barry. Okay. So anyway, a test statistic, this thing along the path to calculating the p-value, is another way of saying, hey, something's unusual here. And in the case of the test of sample proportion, our test statistic is the z-value. All right. So in the case of the free throw shooter, we are going to use this particular formula, that z is equal to p hat minus p divided by the square root of p times 1 minus p all over n. Now here's where the book and I are going to differ a little bit. I would say something like, where are we getting the p hat from? And you would say, oh, from our sample, that 32 out of 50, that's 64%. Where are we getting the p from? 0.8, because of the null hypothesis that we assume is correct. I'm sorry, I didn't quite hear you. Okay. Now, this is where the book and I differ. This is what the book has. P naught. Okay? Okay, so the book says P naught. Why? Because it's the P value associated with the H naught. Okay? So, you got P naught on your scaffolding sheet. I just have P. It's the only P that's running around there. All right? So, calculating the Z value based on what we have. P hat, P naught, if you want to call it that. Where's the N coming from? What's that? Sample size. Okay. So we have everything that we need to calculate this. In the case of the 80% shooter, 0.64 minus 0.8 divided by the square root of 0.8 times 0.2, all divided by 50. In other words, how far are we away from the mean divided by standard deviation, so it turns into how many standard deviations away from the mean are we? And as you can see from their calculation, that's negative 2.83 standard deviations away from the mean. And now, what do we do with that information? Go to the z-table. And what do you get? Well, let me summarize what we've done so far. We're trying to calculate the probability that a p-hat would be less than 0.64. No, less than or equal to. It really doesn't matter. And what we're going to say is that's the same as the probability that a z-value would be less than negative 2.83. And then we say, and Abby, you ready to give me the number? 0.0023. And we call that value that comes at the end of that calculation, the p-value. And now we're ready to make our conclusion. Remember, there were only two conclusions that we talked about. And on the sheet, the one that's headed four-step process for single sample test of proportion, I've got your two mantras there. You'll get the scaffolding sheet for tomorrow's quiz, but you'll eventually have to memorize it. Which of the two conclusions do we have? Do we have the one that says because the p-value is below the alpha value? Or do we use the one that says because the p-hat is above the alpha value? Say it again? What's the alpha value? Excellent question, Jason. Perfect question. I never specified one. And when I never specify an alpha value, we use 0.05. Okay? So if our alpha value is 0.05 and our p-value is 0.0023, what's our conclusion? We have sufficient evidence. Low p-values are good evidence. This one's lower than alpha. So we're using the mantra that starts, because the p-value of 0.0023 is below the alpha value of 0.05, we reject the null hypothesis. There is sufficient evidence to suggest that the true proportion of shots made is less than 80%. Okay, let's put it all together. Okay. No, I don't want that anymore.
Move the trash can.
Yeah, I'm throwing away some stuff there. All right.
You're a tricky guy.
All right. So, the p-value, the probability that we would get this outcome by pure chance alone, assuming H0 is true, is so small, 2 in 1,000, that we believe that that low probability is the evidence that we need to say the initial claim was false, that H0 is not true. All right. So, I want to do this whole problem one more time. I want to do it using the four-step process, and I want to model exactly what I want you to write. The scaffolding sheet is in front of you, but here's how it looks when you do the quiz. Four-step process, give me your 4 boxes. Step 1. I need you to specify what population are we dealing with. Fedors, free throws. What's the parameter that we're investigating? Proportion of free throws made.
There's some tools at the door.
What are they doing out there?
I think they do being tools.
Okay. All right. That's enough. All right. Again, what's our H0? We're saying assume the population proportion is 0.8. Why are we saying that? Because we don't think it's true. What do we think it's true? That P is less than 0.8. Lastly, according to the scaffolding sheet, the last thing we should say, what's our alpha value for this test? We're going to use alpha is 0.05. So there's step 1 done, complete. That's a symbol for, yeah, it looks like a little fish. All right, step 2. Step 2, conditions. Is our sample unbiased? Okay, and I'm going to assume the 50 shots are a unbiased sample. Second condition was independent. We believe the shots are independent, meaning that a shot being made earlier doesn't affect the probability one way or another of the next shots going in. And then last, we talked about normal. Does n times p, which means 50 times 0.8, which is equal to 40, is 40 greater than 10? We get a check mark there. Is n times 1 minus p, which is 50 times 0.2, which is equal to 10, is 10 greater than or equal to 10? So it looks like we meet all our conditions. On to step 3, the calculation step. Z is equal to, we're going to calculate the test statistic first. Z is equal to 0.64 minus 0.8 divided by 0.8 times 0.2 over 50. And we calculated that it's 283. Probability that p hat, can I see your scaffolding sheet? Do I put the p hat notification on there? No, I don't. I just go right to the z. Okay, a model is the way of scaffolding sheet. The probability that z is, okay, now, again, on the notation issue. The 0.8 is pulled directly from H0. The direction of the inequality arrow that I'm going to write here is pulled directly from HA. And we calculated that as 0.002 something. I think that's close enough. So, in step 3, I've got calculation of the test statistic, the z-value, and I've got the calculation of the p-value. And then lastly, I've got everything done. It's ready for the conclusion. Because the p-value of 0.002 is below the alpha value of 0.05, we reject H0. Okay. The last statement is the one that brings in the context of the problem. There is sufficient evidence. I'm sorry. Question? Is there a misprint?
No, but no. The first one doesn't say there's sufficient evidence.
It says we believe the true. Yeah.
Oh, okay. Okay, I'll go with I'll model what's on the sheet. So instead of there is sufficient evidence, we believe the true proportion. Hello.
Hello.
Yeah, girl.
Okay, thank you.
Okay. We believe the true proportion of free throw
We want one too,
shots made is below 0.8.
This is pretty easy.
Okay. So the four-step process doesn't look much different than what we had before. We just have this new mantra at the end claiming on whether we're going to reject H0 or not reject H0. Now, the other thing I need to show you is I showed you how to do this calculation by hand. But one of the things that our calculator does really, really well is to do that all on its own. So, I am not going to force you to calculate the z-value by hand doing a fraction that has a fraction within a fraction and a square root, because only bad things can happen when you're trying to do that calculation. So, if you don't mind, get out your calculator, please. Go to the stats menu. Look under the tests menu. And now that word test actually makes sense because now we're testing a claim. And we got a bunch of different options here. The one that we just did, is called a one-prop z-test. One meaning we use one sample. Prop meaning that we're testing a proportion, not an average. And test because z because we're using the z distribution, and test because we're testing a claim. All right, and it's a fill in the blank. What is our P naught? 0.8. Okay. Now, what is our x? X, we haven't used the letter X all day.
Is it P? Is that P?
No. Cody just said it. Oh, sorry, Perry, one of the two just said it. 32. It's the number of successes that we had. The number of successes out of how many trials? 50. Okay, let's take a look at this next line. Prop not equal to P naught, less than P naught, or greater than P naught. We're trying to prove that a proportion we think is actually less than 0.8. So this part, now we'll get a very different answers. So This proportion refers to the proportion in the alternate hypothesis. This P0 refers to the 0.8 that we wrote in the alternate hypothesis. So do we think P is not equal to 0.8? Do we think that P is less than 0.8? Do we think P is greater than 0.8? Less than. Enter. And then we go calculate. Right? And so what do I demand of you in step 3? You got to write down the z value. And using the right notation, you got to write down your p value. Where's your p value? Right there.
So we don't have to write anything else out?
So what I'm saying, if you use your calculator to do this, here's what your step 3 looks like. Z is equal to negative 283. The probability that z is less than negative 283 is equal to 0.002. That is sufficient for your step 3 now. Are you okay with that?
Yeah.
All right. Everyone understand? Is there anything on the scaffolding sheet that doesn't make sense to you? All right.
Why is the p-value like that number or greater?
That's a really great question. Let me restate the question so everyone can hear the question and the answer. Okay, Rachel asked this question. Why are we calculating the p-value on the question that value or greater, or that value or smaller? Okay, in the definition of p-value, I've got the answer, that result or more extreme. Okay? Not exactly getting exactly 32 out of 50, but rather 32 out of 50 or even worse. Now the reason why we do that is because there's a really odd thing that happens with probabilities. Let's say I flip a coin 500 times. I'm going to ask you a simple question. What is the most likely outcome if I flip a coin 500 times and I count up how many heads? 250. Right? I agree. So you would say 250 is a pretty common occurrence. Well, I'm going to go not back to that, but I'm going to go back to, where's my calculator? Is it there? There it is. Let me calculate using second distributions, binomial, because it's a binomial situation. Let me calculate the probability on 500 coin flips that I get exactly 250 of them. Doesn't that strike you as odd? Getting exactly 250 heads, which is the most common thing to happen, is also rare. So when someone flipped a coin and they said, I got 250 heads, would you say, oh, that's really odd? No. Okay, so what happens if I ask this question? What's the probability of getting 250 heads or less? All of a sudden that number balloons up to 50%. So because individual occurrences may be rare, we lump them with all those occurrences at that level or more extreme to get some value that makes sense.
But how do you know what more extreme is, like less than or greater than?
Well, another great question, Rachel. So how do I know whether the more extreme is less than or greater than? And the answer is, think about what Jason's wanting to prove in this instance. He doesn't want to prove that I'm a better free throw shooter than 80%.
I'm pretty sure worse free throw shooter than 80%.
And I can tell you, you're absolutely right.
And this proves it.
And this proves it. Okay. Embedded in what he's trying to prove, that idea shows up right here in the alternate hypothesis. that inequality sign, the direction of that inequality sign, then gets transferred to that inequality sign when we're calculating the probability. So it's a question always of what is it that we're trying to show? What is it that we're trying to show? And that leads to which side of that value are you going to shade in? Any other questions on this? 4-step process, scaffolding sheet, everything's really, really clear. If it is, then I need to go on to the next page. Okay. Let's see if there's anything here that we didn't cover. I'm sorry? No, there's I got to tie 2 more things together. All right. So, in summary, we have this new thing called the test statistic. For sample proportion, that test statistic is a z. That's new. Also new is the idea that the kind of alternate hypothesis you have leads to shading in to part of a normal distribution. If the alternate hypothesis is p is greater than p naught, then we're going to shade in and we're looking at the area under the curve above. If it is p is less than p naught, then it, like we just did in the free throw example, you get a z value and you're shading in below. And then the last situation is, what if we don't know about the direction? All we do is suspect that there's some difference. This is the third null or alternate hypothesis, the hypothesis that p is not equal to p naught. What do we shade in there? Well, in that case, we're going to end up shading in both below and above the absolute value, or above the absolute value of z and below the negative absolute value of z. We get 2 tails shaded in. We get twice as much probability, typically, when we have a 2-tailed test. You did not have permission to invade my personal space. All right. He just took his z value up to 4.5. All right. So, just one more warning. When can we use these tests? Only when the conditions are met. And a big one of the conditions are we have to know that we expect at least 10 successes and 10 failures. Otherwise, we don't have a normal distribution. Then all of a sudden, the use of the z value makes no sense. So remember, it's got to come from a z table, or we want to use the z table, so we need to meet this condition. If we don't meet this condition, we put the 3-letter acronym. We proceed with caution. And I think it's on your scaffolding sheet too. Would you check your conditions on your scaffolding sheet? It says something like, if you don't meet this, PWC. Okay. Also remember, when we're sampling without replacement, which is a typical way of sampling people, in order to get the independence condition to be met, we need the population to be at least 10 times the sample size. Any questions on this slide? May I continue? What's that? Thumbs up. Great. All right. Let's revisit potato chips. Because you guys tend to work well most with examples, let's do another example. Okay, we've got the potato chips again. Truckload of potatoes comes in. Our tolerance for blemishes on those potatoes is 8%. We take a random sample of the potatoes. 500 potatoes are sampled from the truck, and 47 of them have blemishes. Do we reject the load of potatoes, Or do we say bring them in and let's make some chips?
We got C.
We got a C. What's our procedure?
First we gotta see what the parameter is.
Okay. Population and parameter is our first two steps.
Population would select the potato chips.
Nope. Close. You're half right.
Truckload of potatoes.
Okay. Potatoes.
Truckload.
Did I spell potatoes? No. Okay. Potatoes from truck. Potatoes in the truck. What's our parameter of interest? And I'll give you a hint. It starts with.
Potatoes with blemishes.
Say that again one more time.
Potatoes with blemishes.
We need one more. We need one more word. Take a look at your scaffolding sheet. What's the word that follows parameter colon? Proportion. We have to say how we're measuring the proportion of potatoes with blemishes. Okay. What else do we have? What else do we have to specify in step 1? H0 and HA and alpha. By the way, I always do H0 colon because there's going to be an equal sign in there. I always say HA colon because there's some other relational operator going on there. What's our H0? P is equal to 0.08. What is HA? We're going to reject the potato chips if the proportion is shown to be bigger than 0.08.
Alpha is 0.05.
Alpha? No, not in this case.
0.1.
They specified a different alpha here. I'm just kind of looking around the room. It's like I see so many people having conversations. I would love to believe that those conversations are about statistics and you're so very involved in there and you're seeing all the applications of where this fits into your life. Especially if you're doing big science projects, if you're thinking about going into political science or sociology or psychology, that you're saying, oh my gosh, this opens up an entirely new set of ideas for me. I'd like to think that's going on, but somehow, probably not.
This is actually my major.
All right, let's go on to step 2. What's our conditions? Unbiased. By the way, if you happen to read the book, which is not a bad thing to do, they don't use the word unbiased here. They use the word simply random. I think that misses the point. The reason why we want the sample to be random is so that the sample is unbiased. So I think it gets things confused. So, do we have an unbiased sample? Yes, because it was a simple random sample of potatoes. Check mark. Just a random sample? So it's random sample. Check mark. Okay. What's the second condition? Independent. Since we are sampling without replacement, this is where we're going to use is the population size greater than or equal to 10 times our sample. Do we believe that there are, 10 times the sample is 10 times 47. Oh, 500 samples. 47 have blemishes, sorry. So 10 times 500. Do we believe that there's more than 5,000 potatoes on that truck? And the answer, okay, by the way, this is just a function of where I grew up. I grew up near I-94. And off of I-94, there is a Frito-Lay potato chip plant. And I grew up in Taylor, which is a city on I-94. In Allen Park, there's a Frito-Lay plant. The delivery of the potato, you could actually see when the potato trucks came in because they delivered them in large, full semi-trailers, and they have this thing where the truck backs the trailer up, and then there's a hydraulic thing that essentially takes the entire truck and tilts it to empty it. So you have to think about potato trucks are actually big semi-trucks. Do you think there are more than 5,000 potatoes on the potato truck? Yeah. So we'll give a check mark there. Lastly, normal. Well, N times P, which is 500 times 0.08, which is 40. 40 is greater than 10. The number 47 is going to come into play when we find P at. Good question. Okay. N times 1 minus P, which is 500 times 0.92, which I believe is going to be 460, which is greater than or equal to 10. Okay, we have normality. I got no interest in doing the calculation by hand. So where do I go? Stat. Test. One prop z-test, which is option 5. P0. It's the value from our null hypothesis, 0.08. 0.08. X. 47. There was the number of the potatoes in our sample that had blemishes. N. 500. And what's our alternate hypothesis? Not equal to, P is less than 0.08, or P is greater than 0.08. Well, revisit what we wrote down for null hypothesis. Or, sorry, alternate hypothesis. We wrote, we wrote down this for our alternate hypothesis. P was greater than 0.08. We're going to reject the load of potatoes if what we think the true proportion of blemishes is bigger than 0.08. This thing was our P0, right? So this thing is P. P greater than P0. And calculate. Our p-value. Okay. Again, what do I need you to? What do I need you to copy over to the other side? I need you to copy. You know what? Let's add p hat for good measure. Our p hat was 0.094. Our z value was 1.15, and the probability that z was greater than 1.15 is equal to 1.24. Okay. If I got all that down, we're ready for step 4. Only 2 options in step 4. Which one are we going to end up with? Here's P compared to alpha, it's above. Because the p-value of 0.124 is larger than 0.1, sorry, the alpha value of 0.1, we fail to reject H0. Now we need a context statement. There is insufficient evidence to suggest the true proportion of okay. I'm trying really not to get angry at all the talking that's going on here. I've asked you the question before. Have I been rude to you? Have I done something to you, except present statistics, which can be a dry topic? Have I done something to you to deserve your rude behavior back? I'd really appreciate it if it stopped. This is not easy to learn, certainly not easy to teach. All right. So much of the slideshow contains them doing the same thing that we just did on a single page, using our scaffolding sheet as a guide. There's only one more topic that we really need to hit, and that is this idea that there's a connection. Come on. Page 13. That there's a connection between confidence intervals and two-tailed tests, or two-sided tests. And I'm going to just hit that high point because we're almost out of time. All right? The last example they do in this section is an example where they say, we want to determine whether the smoking incidence in our high school is different than the national average. Not greater than, not less than, simply different. And they do a two-sided test. In a two-sided test, we end up calculating the probability in both tails. Now your calculator, by the way, will do this automatically if you choose the not equal option in the calculation line. Now, if you do a two-sided test, there is this relationship with the two-sided test and the confidence interval. Okay, we know that if our p-hat lies in here, that would lead to the conclusion, fail to reject. Sorry, no. If it's really extremely away, it's a reject H0. Okay? If it lies in here, it leads to a confidence interval like we calculated in the previous chapter that extends both ways. When the p-hat would lead to a reject H0, the confidence interval is so, the p-hat is so far away from the real mean that it never gets back and actually captures the real mean. We had a test question in Chapter 8 almost exactly like this. You calculated the confidence interval for DRP scores for Henrico County. And the last question was, is this evidence that they're different than 32? And 32 wasn't in the confidence interval. We said, yeah, this is convincing evidence that their scores are different than the national average. This is that same idea. When you're in reject land, the confidence interval never gets back to the mean. When you are in fail to reject land, the confidence interval is close enough to the mean that it would cross the mean. So, when you look at a confidence interval that includes the mean that you're testing against, the H0, the proportion you're testing against, the H0 proportion, the P0. If the confidence interval would include that P0, you're in a fail to reject area. There isn't convincing evidence that the real P is different than the P0 T. When your confidence interval doesn't include P0, you are really far away. And that is convincing evidence that you should reject, that the P0 claim is false. All right, you've got homework to do, you've got a scaffolding sheet, you've got the quiz tomorrow. We'll see you tomorrow.
Sounds good.